Greetings, gang. Welcome back. This is your lecture video for chapter 27 and color. I'm going to boil the entire chapter of color down into basically a single statement. Color means essentially wavelength, or if you prefer, frequency of light. We experience color because our eyes receive light and our brains interpret a signal that the eye sends it as blue or red or green or what have you. But it only sends a signal to the brain if the light of the right frequency or wavelength stimulates it. If you remember, we talked very briefly last time about the rod and cone structures in your eye. Those sense light intensity and color or wavelength. And they're only stimulated by the right wavelength because the cone structures have different sizes. And so only the right color, the right wavelength of light will actually stimulate it and send the color signal to your brain. So, why is it that we experience different colors? Well, some objects absorb only some wavelengths of light, and the wavelengths that get reflected are what we see, the ones that actually get to your eye. You ever notice that white clothing shows more detail? White clothes reflect almost all of the light that hits it, and that's why you want to wear white on a hot day so it doesn't absorb a bunch of that light energy as heat and raise the temperature of the clothing and therefore you. That's why people who are shy about their height-weight proportionality wear black because it shows less detail. Either that or because it's a winter day and you want to do the wise thing and wear black on a day when it's colder so that you can absorb more light from the sun. But why do we see green plant life? Well, the plants reflect the green light to our eyes. We call this selective reflection. Now, I had hoped to give you a color filter demo, but I was unable to do that, of course, because nobody has, color filters and light fixtures specifically built for them sitting around their house. Those are all in the lab. But I have taken the liberty of putting a link to the color videos, additive colors and subtractive colors, posted by one of my former professors, Dr. Alejandro Garcia from San Jose State, who also worked at DreamWorks as an animation consultant. In any case, he teaches a really nice class on the physics of animation. So he knows a whole lot about light and color and all the ins and outs and how to convey the message very quickly and easily and very concisely. And so while I couldn't give you a color filter demo, this may be a good time for you to pause and view the additive and subtractive color demonstration videos that he's posted. So, long story short, light sources are a mix of colors, right? But they only generate certain colors. You can break down any shade of color into a mixture of the three primary additive colors, or colors from light sources. And so the primary, or additive, colors, these are from light sources. These are red, green, and blue. The secondary colors or the primary subtractive colors, ninja, what are you doing? Those are yellow, cyan, and magenta. The way that this goes basically is that if you add a red, green, and blue light source together, you get white light. And if you add yellow, cyan, and magenta paint or ink together, you get black. These are subtractive, because these secondary colors subtract the various wavelengths of light, their components, out of a light spectrum. Whereas these ones essentially make up the spectrum. You can make pretty much any color by combining these three primary colors. As long as you're talking about a light source and something that subtracts light, like paint or pigment or some kind. Now the sky is not blue because atoms are like tuning forks or bells, as the author suggests. That's crazy talk. And in fact, I've sent you a link to a video about scattering, most notably this thing that we call Rayleigh scattering, which is responsible for the sky looking blue during the day. This scattering is wavelength dependent, and as a result it scatters light that is of a shorter wavelength, bluer in color, better than that of longer wavelengths or redder light. The intensity of scattered light obeys the following relation. Okay, so the intensity is equal to the initial intensity, like light from the source, times 8 pi to the 4th n alpha squared. Don't worry, I'm getting to the important part. Over wavelength to the 4th power times r squared times 1 plus cosine squared theta. Let's not worry about the angle of incidence or any of that other stuff. Let's look at this. You'll notice that there is a 4th power dependence on the wavelength. This means as the wavelength increases, the scattered light intensity decreases very sharply. And so if you have bluer light, it's going to be scattered much, much less than redder light. Let's say you have some blue light with half the wavelength of some really red light. Okay? Then you're probably looking at 2 to the 4, that's 2, 4, 8, 16. So red light will get scattered 14 times as much as blue light. So the blue light just kind of gets through. Now, strangely enough, this is the same reason that sunsets are red. Short wavelengths of light get scattered by the atmosphere, so the longest, reddest wavelengths get through. As the sun gets lower in the sky, the sun has to go through more of our atmosphere, so more of the other less red colors get scattered more, the blues and so on. Clouds, of course, are white by contrast because the water that makes up the clouds gets scattered evenly across all wavelengths of light, but that's not that interesting. In any case, what makes up the colors of the aurora borealis, or the northern lights? Well, if you ionize nitrogen, then it sort of has its own special spectrum, and if you excite the oxygen and nitrogen in the atmosphere, the electrons in those atoms are going to excite the higher energy states, and as they de-excite and drop back down to a more stable energy configuration, they're of course going to emit photons. And that's why the colors of the northern lights are all the colors that belong to the nitrogen and oxygen spectra. Thus the particles that interact with the Earth's magnetic field are energetic enough to ionize and excite the particles in the atmosphere. Now I've included a picture of the prismatic springs. There are actually something like 9 or 10 places across the Earth that have this really crazy thing, but the picture that I've included corresponds to the one at Yellowstone National Park. So if you want to go there, you can actually see it. In any case, they look really crazy, right? They're blue in the middle, and then sort of green near the edge, and then yellow at the edge, and then orange and red outside, right? So why could that possibly look the way it does? Well, the blue is for the same reason that lakes and oceans appear blue. The blue light doesn't get absorbed by the water like the red and yellow light does so much. What about the green and yellow and red? Well, as we proceed upward, the water in the hot springs that is actually responsible for this entire phenomenon, right? This only happens at hot springs. As we get closer and closer to the surface, the water gets cooler and cooler, right? We're getting further away from the heat source. And obviously at the surface, the water is able to shed the heat. In any case, that makes different thermal layers at which different bacteria undergo photosynthesis, right? And other processes. So the yellow is this Synococcus bacteria that actually photosynthesizes. But the orange layer uses a different chlorophyll and therefore has a different color. And the red-brown layer is more of like a mix of bacteria that have all kinds of lower heat tolerances, and so it doesn't appear to be one uniform color. Okay, I hope you've enjoyed this video. I'll see you again for chapter 28.